So, let's see if I can get to there it is. Alright, let's try this again. Share. Now am I sharing my screen? Alright. Still see my screen? Yes, okay, cool. Good. Alright, so the previous lecture was talking about basically finding eigenvalues and finding eigenvectors. This one hopefully will, and probably I will continue this discussion on Friday as well, but hopefully this will give you a little bit of insight into why we even care about such things. But before we get to that point, let's do a little bit of background that we need to get done. So we're going to do this theorem first to talk about having distinct eigenvalues of a matrix and then looking at the eigenvectors that are associated with these distinct eigenvalues. So if we have our distinct eigenvalues and then we have our eigenvectors to go with those eigenvalues, then it turns out the set of those eigenvectors must be linearly independent. So let's talk about how this proof goes. So certainly we know from the definition, hopefully we know from the definition that we did in the last lecture, that an eigenvector necessarily has to be a non-zero vector. So since V1 is non-zero by definition, if I do the set of just the one eigenvector, the V1, then that's a linearly independent set. It's all by itself. So the idea behind this proof is that we're going to go through the set V1 out to VR and start going from left to right, throw vectors in, and if we get all the way to the end and it stays linearly independent, that's cool. That's exactly what we want. So we're going to go by contradiction and say, well, let's suppose that the set's linearly dependent. That means that as we go through, if we just think about throwing vectors in, if I throw in V2, either that set is linearly independent or it's not. If it is, then throw in V3. Either that set's linearly independent or it's not. If it is, then throw in V4 and continue in this fashion. If we assume that the overall set is linearly dependent, then there must be some vector, some last vector that we enter into the set that gives us a linearly independent set, but the next one we throw in is linearly dependent. So again, if the whole thing is linearly dependent, then at some point, as we're throwing in new vectors into this linearly independent set, we have to switch it from linearly independent to linearly dependent. Because again, that's the only two choices we have for a set. It's either linearly independent or it's not. So if we're saying the whole big set is linearly dependent, and the smallest set that we can form with one vector in it is linearly independent, at some point along the way, we had to switch from a linearly independent set to a linearly dependent set. All right, so this is just our definition for linearly dependent. So remember, linear independence has to do with linear combinations that give you the zero vector. So if it's linearly dependent, then there have to be scalars that aren't all zero that give me a linear combination that is the zero vector. All right, so if it turned out that the CK1 was zero, then this vector, the CK1, VK1, would go away, which would mean that then we would have a linear combination of the V1 out to VK that gives us the zero vector. But remember, we were saying that set's linearly independent. So if that linear combination is the zero vector, then all of those constants would have to be zero, which would force then all of the constants to be zero, which we're saying they're not all zero. So when I'm talking about this set that's not all zero, the set of the C1 out to the CK not being all zero, it absolutely has to be the case that the last one is not zero. All right. Now I referenced this equation by star because I needed to go back and talk about it again. I don't think I'm going to talk to the equation. I mean, I'm crazy, but I'm not quite that crazy yet. So multiply both sides of this equation up here, the star equation, by a. So just multiply it on the left and on the right by a. Of course, on the right, I'm still going to get 0. On the left, we can distribute the a through and pull the constants out. And now this is where your eigenvalues come in. Remember that each of these v's is an eigenvector of the matrix A. And the whole point of eigenvalues and eigenvectors is to be able to replace this this matrix multiplication with scalar multiplication. So each of these AV1, AV2, and so on, we're going to replace with lambda1 V1, lambda2 V2, and so on. All right, so I'm going to label that equation with double star. Now, let's go back to the original equation star. So star, again, was just the original linear combination that gave us the 0 vector. Let's multiply it by the lambda k plus 1 now. Certainly, this is just a number times the vector 0, so I'm still going to get the 0 vector on the right-hand side, and I'm just going to move this lambda k1 all the way through. Lambda sub k plus 1, sorry. And just distribute that through to everything. Okay, so remember, the previous equation we came up with had lambda 1 here in the first one, lambda 2 here in the second one, lambda k here in the second to last one. Okay, so we're going to take that equation, the one I labeled double star, and then subtract the one I've just labeled triple star. So if I subtract, we'll have lambda 1 minus the k plus 1. Both of those would be multiplied by the v1. So I'm just factoring out, if you will, a v1. Do the same thing here with the v2. All the way to the vk. Then I've also got the vk plus 1 term over there. That equals 0. Now, of course, this last term is 0, because I just have lambda k plus 1 minus lambda k plus 1. So that term goes away. Now, look what we have. We have a linear combination of the v's that give you the 0 vector. I don't know why I have the same line in there twice. All right. Apparently, I thought that was really, really important that we had a linear combination that gave us the 0 vector. All right, so since we know that we have this linear combination that's the 0 vector, and we know that the v's, the v1 up to vk, is linearly independent, we have to have, those shouldn't be plus signs. That should be the c1 lambda 1 minus k plus 1 equals, this should be an equals, that first plus sign there should not be a plus sign, that should be an equal sign, equals the second, that c2 times lambda 2 minus lambda k plus 1. This should be an equal sign as well. All those plus signs that are in there should all be equal signs. What we're saying here is we have a linear combination that equals the 0 vector for a linearly independent set. That tells you that the constants all have to be 0. All right. Now, we know that from the setup for the theorem, they tell us that each of the eigenvalues were all distinct. Well, if each of the eigenvalues are all distinct, then all of these differences, the lambda 1 minus the lambda k plus 1, the lambda 2 minus the lambda k plus 1, and so on, all of those are not 0. So that tells us that all of the c1 up to ck has to be 0. That's why it was important for those to be equal signs and not plus signs. And then going back to the original star equation, if we plug in all of those things, we get ck plus 1 times vk plus 1 has to be 0, or ck plus 1 is equal to 0, and that's a contradiction because we just said that one couldn't be 0. So what was it that we contradicted? Remember, we started this off by saying that the whole big set was linearly dependent. That gave us a contradiction, so it must be the case that the v1 up to vr forms a linearly independent set. Okay. So, anyway, the idea behind getting these linearly independent vector ideas is the overall goal of this, by the way, is that hopefully when you find eigenvalues of a matrix and eigenvectors of a matrix, you can form a basis for Rn that involves just all eigenvectors of a matrix. Because if you can do that, then you can do some analysis on powers of the matrix, which pops up in doing Markov analysis, if you've heard of Markov chains at all. Comes up in discrete dynamical systems, if you've heard of those at all. If we had more time, those would be topics that we would explore a lot in a linear algebra class, maybe a second linear algebra class, for example, because both of those have lots and lots of applications. Discrete dynamical systems have applications in biology. Markov processes have all sorts of different applications in all sorts of different fields. So the whole point of why we're doing this is that we want to be able to do analyses of these things. All of these things that I'm talking about all involve matrix multiplication. And if you want to do something with long-term behavior, you need to be able to do powers of the matrix easily. Well, powers of matrices are hard because you got lots and lots of multiplications and additions going on. It's hard to do a long-term analysis from that. So instead, if we can replace that with a scalar multiplication, then we can just analyze what happens to the scalar as the power gets bigger and bigger, which is a much simpler thing to do because you've done those kinds of things in calculus class. So unfortunately, we're not going to have time to do all of that, but I wanted to talk about a little bit why we even care about doing such a thing, because this seems like a weird thing that we're doing. At least I think it seems like a weird thing we're doing. So I think it's important to keep in mind why we even care. All right, so that's why we care about these things being linearly independent, by the way, because if we can find a linearly independent set that has to span, then it necessarily has to be a basis, which means that no matter what vector you start with, you could write in terms of those eigenvectors, and then you could start doing some long-term analysis type things. So anyway, that's one of the reasons why we care about such things. I hate talking about math stuff and just doing, well, that's not true. I love talking about math stuff, whether or not it has any applications. But when I'm teaching a class, I hate talking about math stuff and not telling you at least a reason why we even care about doing such things. All right, so to that end a little bit, let's talk about this idea of a matrix being diagonalizable. So the idea here behind this is that a matrix is diagonalizable if we can write the matrix in the middle of this P inverse and P. So P necessarily has to be an invertible matrix, so that when you take the P inverse times A times P, we equal this diagonal matrix D. Now, this gives you, hopefully this gives you a little bit of idea why we care about diagonalizing the matrix. So, notice that I can write A, if I just solve this for A, since P is invertible, I can multiply on the left by P, and on the right by P inverse to get A by itself. Now, let's just look at A squared. This idea continues if you make the powers get higher and higher. But let's just say I do A squared instead of just, let's say, an A to the n arbitrary. Let's just do A squared. So that would be a PD P inverse squared. Of course, squaring just means I multiply the matrix by itself. And then we know from matrix arithmetic type of ideas that I can regroup in the middle. And notice that the P inverse P here cancels out in the middle, and I just get an I. And then at the very end here, I get a P times D squared times P. Okay, so anyway, so notice that the power on the A goes to the power basically on the D, and there should be a P inverse here on the end. There's another typo. There should be a P inverse on this very last term. I just lost it. But notice that the power on the A goes to the power on the D. And notice that the same thing would have happened had I had, say, an A cubed here. All you would have had then would have been another PD P inverse on the end, and the P inverse and the P again would cancel. And you would have ended up with a D cubed here instead of a d squared. So if we're able to diagonalize, I can make the power on the A go to the power on the D instead. And that makes life a lot easier, because when you do a power of a diagonal matrix, all you have to do is just take each diagonal entry to the power, rather than having to do all of the lining up the rows with the columns and doing all those sums. So when I do that particular power, I can just take the power on each of the diagonal entries and do the power of the matrix. So it makes life a lot simpler as far as doing powers. And it's true in general that if I have any integer n here, positive integer if the matrix happens to be not invertible, or any integer if the matrix is invertible, where I can put negative integers in there, this is a true statement if I'm able to diagonalize. Now again, that's the important part, is if you're able to diagonalize. So we're going to spend a little bit of time talking about when we are able to diagonalize. All right, so here's a theorem that tells us a little bit about when we're able to diagonalize, and this is why we cared about linearly independent eigenvectors to start off this discussion. So a matrix is diagonalizable, so that means that we can find that matrix P and that matrix D. So there's two things that you have to find when you're diagonalizing the matrix. You have to find that invertible matrix P and the diagonal matrix D. Those are two things that you have to find, if and only if A has n linearly independent eigenvectors. So let's go through here and see how we do that. Let's suppose first that we have that A is diagonalizable. So it's if and only if proof again. Remember, we have to go both directions, right? Assume the first part, prove the second part, and then assume the second part and prove the first part. So if it's diagonalizable, then I can write that P inverse AP is equal to D, or just flipping things around, I can move that P inverse to the other side so that I get AP equals PD. All right, so let's talk about this matrix P here. I don't know what it is to start with. I got to find it. So I'm just going to say I have some arbitrary vectors P1 out to Pn that are making up my P. However, I'm making a very specific matrix for my diagonal matrix. I'm going to line up my eigenvalues down the diagonal and make my diagonal matrix that way. So each of these lambdas are the eigenvalues of A in this case. And this requires a little bit more algebra stuff that you remember hopefully back from a college algebra class or high school algebra class. We talked about, in the previous lecture, we talked about the characteristic polynomial of a matrix. Remember, that's when you take your determinant of your A minus lambda I, that's your characteristic polynomial. When you do that, when you take the A minus lambda I, you're going to get a polynomial that has a lambda to the n as its highest power. So if you have an n by n matrix A, you're going to get a polynomial that has a lambda to the n as its highest power, and you know that a polynomial of degree n has exactly n roots if you account for allowing complex numbers and account for multiplicities. Okay? So the fact that I can even do this, make this diagonal matrix with your eigenvalues and know that I have n of them total, comes from that idea of polynomials of degree n have exactly n roots, as long as we go to complex numbers and as long as we count multiplicities. That's known as the fundamental theorem of algebra. Huge, I mean, of course it's a huge theorem. Anytime there's the word fundamental is in the name of the theorem, it's probably a big theorem. But anyway, I wanted to mention that because even in your textbook, they kind of gloss over that. They just say, put the eigenvalues in there. Well, the reason that we know that we even have this many eigenvalues comes from the fact that we have that fundamental theorem of algebra. All right, so we want to show that this matrix, or how to form this matrix P and use this diagonal matrix D. All right, so to use this matrix P, I have some arbitrary P here, but I've written it by its columns. Well, I know that if I take A times P, I know that this column, this first column, ends up getting multiplied by every single row of A, and then that ends up in the first column of the product. This second column here gets multiplied by every single row of A, and ends up in the second column of the product. So we can write our product A times P as AP1 as a vector in the first column, AP2 as a vector in the second column, and so on down the line. Okay. Now let's look at the right-hand side. Let's say we have PD is equal to this matrix. Now again, when we match things up, this lambda 1 gets multiplied by everything in the first column of P. This lambda 2 gets multiplied by everything in the second column of P, and so on down the line. So you end up with this matrix when I do the P times the D. Now match up the columns. I have AP1 equals lambda P1. I have AP2 equals lambda P2, and so on down the line. So if I want these things to be equal, then I need my API to be lambda IPI for all of the i's. All right, we know that P is invertible because I already know that this P happens, right? We're assuming that A is diagonalizable. I'm assuming that already that I can write P inverse AP as D. I already know that P exists, okay? And I know it's invertible. If it's invertible from that big mega theorem that we've talked about over and over and over again this semester, we know that the columns have to be linearly independent, okay? And when we have this equality, we also know that each of these P sub i's is an eigenvector. I know they have to be non-zero because I can't get a column of zeros or my matrix wouldn't be invertible. So I know that they're non-zero, and if I have API equals lambda IPI, then I know that each of the P's, each of the columns of P's, is an eigenvector for A, that it's associated with each of the lambdas. So A must have n linearly independent eigenvectors, and they turn out to be the columns of P. Okay, well, usually we don't know that we already can diagonalize the matrix. We're trying to diagonalize the matrix. So the more important part of this proof is the other direction. Finding these, so the fact that we have n linearly independent eigenvectors tells us that we can diagonalize the matrix. That's the important part of this theorem. So let's see if we can go through this one. So let's call the linearly independent eigenvectors P's, and they're associated with the lambdas. And all we're saying with the respectively statement is that the subscripts match up. All right, same setup for P and same setup for D. Since I know that we have linearly independent eigenvectors, I know that P is invertible. That's using the equivalence of all those conditions that we have for invertibility of a matrix. We know that we can invert a matrix if it has n linearly independent columns. So I know that I know that P is invertible automatically. And then going through the same kind of computations that we did before, I know that A times P basically just runs A through the columns of P. But remember how we created P? We created P by using eigenvectors, so we can replace each of those matrix multiplications with scalar multiplications. And then I can break apart that matrix again just by looking at how things get multiplied together. We know that the P's, I can line up the columns of the P's, or the columns of P on the left, and then the eigenvalues down the diagonal on the right. And that must be PD. And then since P is invertible, I can move the P inverse to the other side, and then we have the definition of diagonalizable. All right. So again, the second part of the proof of this theorem is the big part of the theorem. It tells us how we are able to diagonalize the matrix. If we can find n linearly independent eigenvectors, then I can form this matrix P by using the eigenvectors. So let's go through an example. Just as a corollary here, this is when you know that you're absolutely going to be able to diagonalize, is if you have distinct eigenvalues, then I know the A is diagonalizable, because by the first theorem that we proved said that if you have eigenvectors that go along with distinct eigenvalues, the set's already automatically linearly independent. That's why we cared about that theorem to start with. It helps us with this corollary. Now, just because we don't have n distinct eigenvalues doesn't tell us one way or the other whether or not it's diagonalizable. We'll see examples of that later. All right, so let's go through an example here. I said a lot of words, lots of proofs, not many examples. Well, not many as in 0 so far. So let's actually do an honest-to-goodness example and see what's going on. Hopefully it'll help illustrate what we've been talking about here for about a half an hour. All right, so let's start with this matrix A. The first thing I need to do is the whole goal of this is to diagonalize. Well, in order to diagonalize, I got to find whether or not it has, in this case, 2 linearly independent eigenvectors. Okay, I need 2 because I got to form a 2 by 2 matrix. Well, to find eigenvectors, I have to find eigenvalues. To find eigenvalues, I got to solve the characteristic equation. So let's set that up first. So we'll do the determinant of A minus lambda I is equal to 0. And remember, this basically just says take lambda, subtract it off the diagonal, and then take the determinant. Okay, so when I subtract lambda off the diagonal, I get negative 14 minus lambda up in the upper left corner, and 16 minus lambda in the lower right corner. And then we just take the determinant, so we do the product down the main diagonal, subtract off the product off the off diagonal. So we get that particular expression. If you simplify all of that mess, which is actually not all that bad, you get lambda squared minus 2 lambda minus 24. And that factors nicely, because I wouldn't have put one in this lecture had it not factored nicely to start with. So I see that my eigenvalues in this case are negative 4 and 6. All right, so let's see if we can figure out the eigenvectors. So remember, to figure out the eigenvectors, we have to take our eigenvalue, which in this case is negative 4, plug it back into our original matrix where the lambdas are, and then row reduce. So when we plug in negative 4 for lambda, we get this matrix, the negative 10, 10, negative 20, 20. Row reduces to that. I hope I emphasized this enough in the video that I asked you to watch, but if you have an if you have an eigenvalue, the whole point of finding the eigenvalues is to get those non-trivial solutions that we talked about in that particular lecture. If you're going to get that's always trying to solve a homogeneous system. To get non-trivial solutions in homogeneous systems, you always have to have a free variable. In this case, when you're working with a square matrix, in order to get a free variable, you have to have a pivot-free row. You have to have a row of zeros. Okay? So if you get to the point where you've row reduced your matrix and somehow you get the identity matrix, you have the wrong eigenvalue. Somewhere you've made an error. Okay? Either you solved the characteristic equation incorrectly and got the wrong eigenvalue, or if you're using your calculator, you've typed something in wrong. Something is not right. You have to get at least one row of zeros here every time. All right. So the whole point of this was to figure out an eigenvector that corresponds to negative 4. And in this case, it's not too hard to see that it has to be 1, 1, because we would move the negative 1 to the other side when we put in a t here. So you would have a t times 1, 1. And I just need to diagonalize, we just need one eigenvector. We don't need a whole eigenspace. We just need one. Okay. All right, let's do the same thing for lambda equal to 6. If you plug in 6 for lambda, you should get that matrix, which simplifies to the 1, negative 1/2 on the first row. Now again, we just need to pick one eigenvector, and personally I prefer to get rid of the fractions when I can. So if you plugged in a t here, you would get 1/2 t for x1 and t for x2. But remember, t can be anything. So if I make t equal to 2, then I get this vector that's just 1, 2. I'm just trying to avoid the fractions. You can put the fractions in. It doesn't matter. I'm just saying that we can use any constant times that vector, and you still get an eigenvector. So if I can get rid of the fractions, I will. All right, so now let's form our matrices. So going back to our proof, remember we constructed the matrix P by putting in the eigenvectors in for P and putting the eigenvalues in the diagonal, but making sure that since the first column is 1, 1, we use the -4 because that was the eigenvalue associated with that eigenvector. In the second column, I've got the 1, 2, which was associated with 6, which is why that one's on the second diagonal entry. Okay. And now we can check. It's not too hard to check. If you do, I've got the inverse in the wrong spot on the first one. This should be, the inverse should be on the P, not the P inverse. So this is another typo. That's what I get when I do these things in a hurry. This should be the inverse should be on the first part. It's correct on the right-hand side of the equation. And if you run through and do this computation, you get -4,006. All right, so I told you that the whole reason why we care about doing such things, or at least a reason why we care about doing such things, is to be able to do powers of the matrix easily. So let's do a to the -3rd power. Well, using the properties that we talked about earlier, I can take that -3 and I can move it to the d. And it doesn't affect the p or the p inverse. So I've got the 1, 1, 1, 2 for the p. I've got 1, 1, 1, 2 inverse over here for the p inverse. The -3 just goes on the -4 and 6. Then again, the whole reason why we do this is because it's easy now to do this power. We can take this -3 and just move it to the diagonal entries. And if doing this power, all we have to do is just reciprocate and then take the power. So this gives me -1/64, and this gives me 1/216. Remember, 2 by 2 matrices, the inverses are pretty easy. You flip your main diagonal and you negate your off diagonal. That was how I could get this pretty easily. Yeah, oh, you have to divide by the determinant as well out in front, but the determinant here is 1. So, and then if you do that multiplication, you get this particular matrix when we're done. So again, that was the whole reason why we even care about doing this diagonalization for our purposes, is to be able to do these types of powers. And notice that we only really had to do 2 matrix multiplications when we're done, right? This was just doing real number powers. The only matrix multiplications we had to do were these first 2, get the result, and then do the last that result with the last one. All right. So that is, again, why we care about such things. So let's see if we can do another example here. Let's see if I can get to... I need to do something else. Let's see here. Sorry, I gotta get back. I need to get to another screen here. Maybe. There we go. Now I can get to it. All right. Oh, I forgot to add the page. Sorry. I thought I did this last night. Apparently I did not. All right, so we're gonna we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we'll do more of this next time as well, but I just wanted to do, we' do another example so that we can see what's going on. Hopefully get this into the calculator as well, because I want to do another calculator example with you to show you how you can use that to help you find eigenvalues and eigenvectors as well. So zoom in a bit here. All right, so just to summarize what we just talked about in the lecture, to diagonalize a matrix A, we're looking for an invertible matrix P and a diagonal matrix D so that when you do your P inverse A times P, you get D. Okay, that's the whole point. And then, again, to summarize from what we just talked about in the lecture, we can always diagonalize if we can find n, whoops, whoa, that went crazy, n linearly independent eigenvectors. If we can find those eigenvectors, then we can always diagonalize. So let's see if we can do this one. So we have the matrix A, which is this one. So to find eigenvectors, we need to find eigenvalues. So to find eigenvalues, we have to do our characteristic equation. So we need to take our determinant of A minus lambda I oops, I forgot my lambda on that second one. So this is the equation that we have to set up, right? The determinant, just to write down in the symbols again, is the determinant of A minus lambda I equals 0. So we could do this one by hand, but let's see if I can illustrate this again with the calculator. And I need to pull the calculator up, which I should have done before we started. It's all right. I'll get there. Maybe I'll get there. It's opening, I promise. There we go. All right. Let's see if I can organize my screen so I can see it before I share the calculator here. All right, so let's do a new share with the calculator. All right, so let's go to second matrix. I'm just going to put it in matrix A here. A is a 3 by 3. And the matrix was 8, -4, 1, 9, -9, -1, and -18, and 12, and -1. So just type the original matrix A in here. Now again, I want to hopefully use the calculator to help me find the eigenvalues. It gets a little tricky, of course, if you've got fractional eigenvalues, if you've got, well, definitely if you have irrational eigenvalues. At least the 84 doesn't help you very much if you've got irrational eigenvalues or fractional ones. I mean, if you can recognize the fraction, it's fine, but at least it gives you an idea of where these things need to be. So to get that, we'll go up to the y equals, and notice that the way we get the calculator to graph it for us is we'll use the matrix command. I'm going to clear this out so I can show you how we type in the command. So remember, we're trying to solve the characteristic equation. The characteristic equation, again, is the determinant. So we'll go to second matrix and grab the determinant command. Then it's A, or whatever matrix you're trying to find the eigenvalues for, but in this case we put it as A. And then minus, for eigenvalues we usually write it as lambda I. In the calculator I don't have a lambda key, so I'll use the X. And then times. And then we have to subtract off the identity. So again, in your calculator, that second matrix, go over to math. Maybe I'll go over to math. The identity matrix you can make on the calculator using option 5 here. And then you have to tell it how many rows and columns you want. So in this case, it's a 3 by 3 identity matrix. So this gives you your determinant of A minus lambda I. So to help us find where this has zeros, we're going to graph it. And all I really care about is where it's crossing that x-axis. And again, we'll be able to tell when we row reduce if we actually have the right values. You can go in and find the zeros on your calculator if you're not 100% sure where it's crossing. If you go second calculator, you can always find a 0 there. So if we do that, just to show you one of these, the first thing you have to type in is the left bound. So let's say I want to find this one that looks like it's at -1. You move your cursor to the left a little bit, hit enter. Move your cursor to the right a little bit, hit enter. And then put it where you guess and hit enter. So we really do look like it has a 0 here at -1. All right, so again, it looks like that our eigenvalues here are -3, -1, and 2. And again, we should be able to see rather quickly whether or not that's true. So if I go back to our main screen, and let's do matrix, math. I want to do reduced row echelon form. And I want to do the matrix A. And I want to subtract off when we put in -3 for lambda. So I'll do -3 times the 3 by 3 identity matrix. So again, what this, just to go through the command again, this has the effect of taking the -3 and putting it in for the lambda. So we're subtracting -3 off the diagonal. This just saves you some time from having to go back into the matrix and type in a new matrix every time. That's the reason why I'm doing this, so you can save some time and not have to retype things 3 and 4 times. All right, so there's our reduced row echelon form. As I mentioned before, always need to see a row of zeros. Okay, so if I go back now to where we were writing things down, for our lambda equal to -3, we have what for our eigenvector? Well, we have a -1/3 in the first component, a -2/3, -2/3 in the second component, and a 1 in the third component. I know this because, again, just to write this down since the calculator is not on your screen right now, we had 1, 0, 1/3, 0, 1, 2/3, 0, 0, 0 for our reduced row echelon form. Now again, if you don't like fractions, I could multiply everything by 3 here and still have an eigenvector. Still works. Okay. So this gives us our first eigenvector. It's probably because I don't have it maximized. Could you not see what I was writing? Can you see it now? Okay. Yeah, I had the calculator still up on my end, so my screen was only taking up half the computer. That was why I was doing that. Sorry about that. All right, so let's see if we can find the other two real quick since we only have a few minutes here. Let's go back over to the calculator. We said that another one of our eigenvalues looked like it was -1. I can do this pretty straightforwardly. Just hit second entry, bring up our previous entry here, scroll over, and change our -3 to a -1. Again, when you row reduce, you better see that row of zeros. So we've got 1/3 up in the upper left corner and 1/2 here in the second component. So let me go back over to write this down. So for lambda equal 1, or -1 I mean, we had 1, 0, 1/3, 0, 1, 1/2, 0, 0, 0. So our eigenvalue then, or eigenvector I mean, will be -1/3, -1/2, 1. Or again, if you don't like fractions, you could multiply by 6 and get rid of all your fractions. You don't have to. You can leave the fractions in there, really, or you can make really wacky things if you want to multiply it by a completely different scalar. I just prefer to write it without the fractions. All right, let's find the last one here. Go back over to the calculator. One more to get. Second entry. And change, I think we said the last one looked like it was at 2. Looks like it was at 2 to me. So we've got 1/2 and 1/2 in those last two, or the first two entries in the last column. So go back over, write this down. So for lambda equal to 2, we had 1, 0, 1/2, 0, 1, 1/2, 0, 0, 0. So that would give us -1/2, -1/2, 1. Or, again, if you don't like the fractions, multiply by your 2 to clear the fraction. So then just to identify what our matrices are here, your P matrix will be the -1, -2, 3, the -2, -3, 6, and the -1, -1, 2. And your D matrix then would be -3, 0, 0, 0, -1, 0, 0, 0, 2. The interesting, at least one of the interesting things that I find about this particular thing is you could reorder these things around and you still get the same, as long as you match up eigenvector with eigenvalue, the order of the columns doesn't matter. So you could have also done P is equal to -2, -3, 6, -1, -1, 2, -1, -2, or +3. Then your D would have to be -1, 0, 0, 0, that's a 0 on the end, 0, 2, 0, 0, 0, -3. As long as you match up the eigenvector with the eigenvalue, you can order the columns however you want. You can't do that with the rows. The rows have to be the way they are, but the columns you can flip around, and you can check if you do P inverse A, P, you should get D in the order that you choose. So it doesn't matter. Any questions on that at all? The D is the eigenvalues that go along with them. So this one, that was the lambda equals -3, and this was the lambda equals -1. Yep. Oh, good. Other questions at all? Was everybody able to hear me today? Wonderful. Well, I'm sitting out on my deck, and I live on the lake, so I actually have a nice view. It's a nice breeze, and everybody was able to hear me. It was a good day today. Wonderful. All right, cool. All right, well, great. I will talk to you all later. Have a good one. I did post a new assignment as well. I think I mentioned it in the email, but just to remind you, I posted a new assignment. So, everybody have a good one. Yep, bye-bye.